Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section 4.4 on exponential and logarithmic equations. So let's start off with a brief preview of what we're going to see in this section, because there are going to be 4 different types of equations in total, and how you handle each one has to be a little bit different. So it's important that you also be able to spot what type of equation you're dealing with. In total, we're going to be dealing with 2 types of exponential equations. The first is going to be exponential equations with like bases. So either both sides of the equation are a power of the same base, or you can turn it into a power of the same base. We worked some problems of this type back in section 4.1. We're just going to add an extra layer on top of that in this section. And then we're also going to talk about how we handle exponential equations without like bases, when you can't write both sides as a power of the same thing. Then we're going to be looking at 2 types of logarithmic equations as well. We're going to be looking at logarithmic equations without constants, and so that means that everything is either inside of a logarithm or can be brought inside of a logarithm using the properties that we covered in section 4.3. And then we're going to look at logarithmic equations with constants. So when you have numbers floating around outside of the logarithms that you can't pull inside. And we have to treat the problems a little bit differently in that case. One thing that's very important to note for this section is that anytime we're dealing with the logarithmic equations in the second half of the section, extraneous solutions become fairly common. You always have to double check your answers at the end. And in particular, what you want to watch out for is to make sure that none of your answers turn the inside of a logarithm negative or 0, because that's undefined. And if you happen to be solving for the base of a logarithm, which happens more rarely, but it happens on occasion, remember the restrictions for bases. They have to be positive and can't be equal to 1. In example 1, we're going to work some problems involving exponential equations with like bases. And we're going to start off really simple and gradually introduce some more complexity as we go. Starting with part A, we've got 2 to the 2x plus 3 power is equal to 4. So this is a like bases problem because you can write both sides as a power of 2 pretty easily, since 4 is 2 squared. And now, since both sides are a power of the same base, 2, their exponents have to be equal to each other. So 2x plus 3 would have to be equal to the other exponent of 2. It's a pretty easy or linear equation to solve if we just subtract 3 from both sides and divide by the coefficient of 2. We get x is equal to negative 1/2. Keep in mind that, like always, you can double check your answers by plugging x back in to the original equation, which in this case would work, because if you plugged in negative 1/2 for x, the exponent would become negative 1 plus 3, or 2, and 2 squared is in fact equal to 4. Part B adds one extra thing to worry about, because although we can definitely write both sides as a power of 3, the difference is this time 9 already has an exponent. So we have to be careful about how we do this. So the left-hand side is still 3 to the 3x minus 4, but this time, instead of 9 to the x, I'm going to replace 9 with 3 squared in parentheses, and that is still raised to the x power. All right, so if you're breaking something down into a smaller base that already has an exponent, you have to break it down inside a set of parentheses. Now we can use properties of exponents to simplify. Because we know a power raised to a power like this, you just multiply the exponents. So this would be 3 to the 2 times x. And now it works pretty much like the previous problem. We just set the two exponents equal to each other. I'm going to subtract 2x from both sides and combine it with the 3x on the left, and I'm going to add 4 to both sides to move it to the right. And so we get x is equal to 4. This one is a little bit trickier to check because the numbers get a little bit larger here, but you could plug this back into both sides and see that they equal the same thing. If you plug 4 into the left-hand side, you would get 3 to the 12 minus 4, or 3 to the 8. And on the right-hand side, this would be equal to 9 to the 4th. And you could spot check both of those in a calculator pretty quickly to see that they are in fact equal to the same number, which happens to be 6,561. So we did not make any mistakes in solving for our x. Let's take a look at one final variation of this problem type. And in this case, we can't write 16 as a power of 8. I'll see that from time to time. Students will just get in a hurry and they'll write 16 as 8 squared because 8 times 2 is 16, but that's no good. 8 squared is 64, so that doesn't work. But what these are is they're both powers of something in common because both 16 and 8 are powers of 2. 16 is 2 to the 4th power, and 8 is 2 cubed. So what we can do is break both sides down into a base that they have in common. And if you spot this, it'll actually save you a lot of effort because we're going to talk about how you can solve a problem like this by treating it as a non-like base problem, but it makes it much more complicated. So in this case, we're going to break down both sides. Again, being careful to do it inside parentheses. So the 16 would be 2 to the 4th, still raised to the x plus 1 power. The 8 would be 2 cubed, still raised to the 2x power. Now again, we have to be careful because this exponent has multiple pieces. So when I multiply this time around, I need to do the inside exponent of 4 times the entire outside exponent of x plus 1. The parentheses are very important here. On the other side, we're going to have 2 to the 3 times 2x, which will just give us 6x. So now if we distribute through, this would give us 2 to the 4x plus 4 is equal to 2 to the 6 times x. And now, just like before, we can set the exponents equal to each other and solve. Subtract 4x from both sides. Divide by 2. And we get x is equal to 2. Now let's talk about how you handle it if you can't write both sides as a power of the same base. And ultimately it's going to hinge around the power rule that we first saw in section 4.3, which is a property of logarithms, which says that if you have an exponent inside of a logarithm, something of the form log base b of x to the n, you can pull the exponent out as a coefficient, as multiplication. And so since in our exponential equations, the variable we're trying to solve for is in the exponent itself, using this technique will allow us to pull the variable out so that we can then solve for it more like a linear equation. Now, a few things to note here. The first is that you can use any base logarithm that you want to for this technique, but in general, we use common log or natural log. And the reason for that is because in the end, we're going to plug the answer into our calculator so that we can get an approximation rounded to 4 decimal places or something of that nature. And our calculators only have buttons for common logs or natural logs. Oftentimes, with the easier versions of these problems, you can also work them in terms of logs of other bases by converting the exponential equation into the equivalent logarithmic equation, which we did back in section 4.2. That works as well, but be aware, that if you do use that process, if that's what you're used to, you will have to additionally use the change of base formula in order to be able to plug it into the calculator effectively. So the process I'm going to stick to with the examples we're going to work is I'm going to start by taking the natural log or the common log of both sides of the equation. You have to do the same thing to both sides to keep the equation balanced like always. Then I'm going to apply the power rule to pull the exponents out as coefficients. And then I'm going to solve for the variable now that it has been pulled out of the exponent. So just like before, let's take a look at a few examples of this type. Starting with part A, we're asked to solve the equation 5 to the 3x is equal to 29. So I'm going to take either the natural log or the common log of both sides. It doesn't matter which in this problem. So let's say I just go with the natural log. So I'm going to take the natural log of the left-hand side of the equation and the natural log of the right-hand side. Now on the left-hand side, we can apply the power rule, and that exponent of 3x can be pulled out front. And now it's just a matter of solving for x in a linear manner, because the natural log of 5 is just a number. So we can divide it across to the other side, just like we would any coefficient. And so our final answer here would be the natural log of 29 divided by 3 times the natural log of 5. It's important to remember here that we have no property for simplifying the division of two logarithms. This does not simplify. It's as good as it gets. In some problems, you might be asked to plug this into a calculator and round the answer to 4 decimal places. If you do, be a little bit careful about how you enter it into your calculator. Anytime you have more than just a single number in the numerator or denominator of a fraction, you want to put parentheses around it so that your calculator keeps the order of operations straight. You're basically telling your calculator to multiply these two things in the denominator together, and then it will be divided by all of that, which in this case would give us a number of about 0.6974. Again, you can double check this by taking it and plugging it back into the original equation. Although be aware, if you do round it to 4 decimal places and you plug in 5 to the 3x, you might get a number that is not quite 29. It will be really close to 29, but because you rounded this answer, it will be a little bit off. Whereas if on your calculator you use the second answer button for the x value so that it carries all of the decimal places over, you will probably get exactly 29. Or at the very least, something extremely, extremely close to 29. For part B, the choice of logarithm becomes a bit more important here. Most of the time, it doesn't matter whether you use natural log or common log. Either one will get you the same result. In fact, if you swap out both of these natural logs with common logs in the previous example, you would get the exact same result. Because although common log of 29 is not the same as natural log of 29, once you take it together and combine it with the common log of 5, it all balances out to the same final answer. That said, if you see that you have a base 10 or a base e in the problem, it will make your final answer look a little bit nicer, and it'll work out a little bit easier if you use common log and natural log respectively. And the reason for that is because then we can take advantage of the inverse properties that we first introduced in section 4.2, where if you have common log of a 10 to the x, log base 10, exponent base 10 will cancel each other out. And similarly, if you take natural log of a natural base e, log base e and exponent base e will also cancel each other out. So for part B, because we have an exponent base of 10, common log is the better choice here. Natural log will still get you to the right answer, by the way. Your right answer will just be harder to plug into a calculator. It won't look as nice. So if we do take common log of both sides of this equation, so we have log of 25 is equal to log of 10 to the negative 2x. Instead of having to apply the power rule and pulling that negative 2x out, instead we can just apply the inverse rule, cancel out the log base 10 and the exponent base 10, and the negative 2x is all that's left. And now in order to solve for x, all you have to do is divide by negative 2. And so x would be equal to negative log 25 over 2. Similar for part C, because we're dealing with a base e in this problem, it'll be a little bit easier if we take the natural log of both sides. So we have natural log of e to the x is equal to natural log of 2 to the x plus 1. And this problem has a little bit of extra complication to it. On the left-hand side, natural log and e cancel each other out, and the exponent of x is all that's left. On the right-hand side, however, we have to apply the power rule. So I'm going to pull out the exponent, but be careful. Whenever you have an exponent with multiple pieces like this, when I pull it out, it's going to be the entire exponent, x plus 1, times the natural log of 2 that's left over. And now a lot of students get stuck with this type of problem because they're not sure how to solve something like this for x. Well, what we're going to do is use a technique that we first introduced all the way back in section 1.2 when we were solving formulas for a specific variable. And that is, we're going to multiply everything out so that we don't have any parentheses left. We're going to group up the terms with x next to each other, and we're going to do the greatest common factor. We're going to factor out the x in common. And that's the trick to solving this. So if I want to get through these parentheses, I'm going to distribute the natural log of 2 through the equation. So we get x is equal to, we're going to have x times natural log of 2 plus 1 times natural log of 2. Now I'm going to group up the x's together. So I'm going to subtract that x natural log of 2 over to the left-hand side. And now I'm going to factor out the x in common. So if I pull an x out of both terms, divide an x out of x, you're just left with 1. Divide an x out of x ln 2, you're just left with the ln 2. And now we can just divide that whole parenthesis across to the other side. And so our answer would be x is equal to ln 2 divided by 1 minus ln 2. Now, if you are asked to plug this into your calculator, again, you've got multiple things going on in the denominator of this fraction, so you would want to make sure that you put extra parentheses around that subtraction. Let's take a look at one more example so that we really make sure we understand the trick that we just used in the previous problem. So this one is pretty similar, although now there is no base 10 or base e, so it goes back to not mattering whether you use natural log or common log. So with that said, try pausing the video here and see if you can solve this equation for x. So I'm going to start by taking the natural log of both sides. I tend to prefer the natural log just because it's one less letter to write, if nothing else. And now on both sides of the equation, I'm going to apply the power rule. So I'm going to pull the exponents out, multiply them by the remaining natural logs. Right, we've got the same issue here. We need to solve for x, but it's tangled up in multiple places. Multiply everything out, collect next terms like to each other, factor out the x. So I need to get rid of the parentheses again. So this is going to be x times the natural log of 3 minus 1 times the natural log of 3. I'm going to subtract the x natural log of 3 over to the left. You could also group up the x's on the right as well. Your final answer would just have all of the signs being different, but it would still be the same. It's like multiplying both the top and the bottom of the fraction by -1, which is equivalent. Factor out the x in common. And then we can just divide the entire parentheses across to the other side. And so we have x is equal to the negative natural log of 3 over the natural log of 2 minus the natural log of 3. If these were all common logs, it'd be the same thing. Again, if you want to plug this into your calculator all in one go, you would need parentheses around the denominator because there's multiple things happening down there. Subtraction, if you had addition, if you had multiplication, you need parentheses. So now let's talk about the first type of logarithmic equation in the section, and that's the logarithmic equations without constants. And again, that means that everything is either inside of a logarithm to start with, or it's a coefficient that you can pull in as an exponent using the power property. The idea is if you can manage to write both sides as a single logarithm of the same base, something of the form log base b of x is equal to log base b of y, then you can apply something called the one-to-one property of logarithmic functions, which is very similar to what we were doing with exponential equations with like bases. The idea being, if log base b of x is equal to log base b of y, since log base b is doing the same thing to both sides, the only way these two things are equal to each other is if the stuff inside of the logarithms is equal. So you can set the inside of each logarithm equal to each other, and then it's the same. So in order to solve, the first step is that you have to write both sides as a single logarithm. And I put that on bold because a lot of students forget that. In a lot of our problems, we're going to start with 3 or maybe even 4 logarithms. You cannot just drop all of the logarithms in a problem. That does not preserve equality. You'll be changing the equation into something different. You have to have one logarithm equal to another logarithm, and that's it, nothing else. Once that's done, you can apply the one-to-one property to set the stuff inside each logarithm equal to each other. And then you can solve the resulting equation for x. Now, something to watch out for is that you always have to check for extraneous solutions when working logarithmic equations. It's a good idea to check your answers for all types of equations. It is mandatory for you to check your answers with logarithmic equations because you will get false positives sometimes. So at the end of each problem, you take your answer, you plug it back into the original equation before you started manipulating things. If it makes the inside of any logarithm negative or 0, that is something that is undefined, so you throw it out. If it keeps the inside of all of the logarithms positive, you're good. You get to keep the answer. So let's take a look at some examples of logarithmic equations without constants. So to start things off, we want to solve the equation natural log of x plus natural log of x plus 2 is equal to the natural log of x, or 8. Again, you cannot just drop all 3 of these natural logs. Very common mistake. It does not work. You have to get a single logarithm on both sides of the equation. And that's why we talked about those properties in section 4.3. So what we have to do is combine these 2 logarithms on the left together. And the sum of 2 logarithms, addition on the outside, is multiplication on the inside. So this would be the natural log of x times x plus 2. And be careful with the parentheses there. This is now equal to the natural log of 8. Now that we have a single natural log on both sides, we can apply the one-to-one property. The only way these two natural logs can be equal to each other is if the stuff inside the natural logs are equal to each other. And at this point, we actually end up with a quadratic equation to solve. Because this is x squared plus 2x is equal to 8, or x squared plus 2x minus 8 is equal to 0. And quadratic equations pop up fairly frequently in the process of solving logarithmic equations. So make sure you brush up on your strategies. Factoring, quadratic formula, completing the square, it's all viable. In this case, we have a quadratic equation that's relatively easy to factor. So this is going to factor into x plus 4 times x minus 2. As always, when you factor, you should double check. This would be x squared plus 4x minus 2x, which would be a plus 2 minus 8. So this is the correct factorization. Now I'm going to set both of these equal to 0 and solve. Which would give us x is equal to negative 4 and x is equal to positive 2. We're not quite done though. You have to check your answers. And so if we take this x of negative 4 and we plug it back into the original equation, that very first natural log would be the natural log of negative 4, which is undefined. Negative 4 is what we call an extraneous solution. It doesn't work. Whereas on the other hand, if we plug in an x of 2, we would get natural log of 2, which is okay. And in the second one, we would get the natural log of 2 plus 2, or natural log of 4, which is okay. So 2 keeps the inside of the logarithms positive, so that one checks out. So our one solution to this logarithmic equation would be positive 2. So let's take a look at another one. In part B, we've got log base 3 of x is equal to log base 3 of 2 minus log base 3 of x minus 2. So once again, the first thing that we need to do is get a single logarithm on both sides of the equal sign. So on the left-hand side, we're good. We've got log base 3 of x. On the right-hand side, this time it is the subtraction of two logarithms, so it's going to correspond to division on the inside. So this would be log base 3 of 2 divided by x minus 2. Now that we've got a single log on both sides, we can set the stuff inside equal to each other. So this rational equation we want to solve by getting rid of the fractions. We're going to multiply both sides by x minus 2. And by the way, if you really don't like having the division at all in the problem in the first place, you actually could have added this log base 3 of x minus 2 over to the left-hand side of the equation. Then it would have been the sum of two logarithms, and you would have gotten multiplication instead, which still would have given you x times x minus 2. So you would have just started at this step. So I'm going to distribute this through now. This is x squared minus 2x is equal to 2. Now I could subtract the 2 over to the left-hand side, set it equal to 0, but we would find that this is one that doesn't factor. So our choices now are either completing the square or the quadratic formula. Because the coefficient of x squared is 1 and the coefficient of x is even, I'm going to use completing the square here because this is going to be a pretty straightforward problem. So in this case, what I want to do is take b, the coefficient of x, divided by 2, cut it in half, and square it. So that would be a negative 1 squared, or a positive 1. So I add that to both sides of the equation. The left-hand side now factors into x minus 1 quantity squared. It's always the b over 2 before you square it. And that would be equal to 3. Take the square root of both sides. And then add 1 to both sides. So we've got two possible answers. 1 plus the square root of 3 and 1 minus the square root of 3. We do have to check our answers though. And in order to make that easier, it's definitely worth turning these into decimals so that we can get a better idea of what we're working with. So 1 plus the square root of 3 is about 2.73, and 1 minus the square root of 3 is about a negative 0.73. Well, already that gives me trouble, because if I take 1 minus the square root of 3, which is a negative number, and I plug it back into this first logarithm, we get the log of a negative number, which is not okay. So that one's out. It also wouldn't work in this last logarithm, by the way. But it just takes 1. So that just leaves 2.73. Is that okay? Well, log base 3 of a positive number, 2.73, would be fine. And if we plug it into this one, it gets a little bit close. But 2.73 minus 2 is still positive. It's still a positive 0.73. So that's okay as well. So we do get to keep this solution. The inside of all of the logarithms is still positive. So we have one solution again as our final answer, and that would be 1 plus the square root of 3. Let's take a look at one more logarithmic equation with no constants. And so this time we've got natural log of x minus natural log of x plus 1 is equal to the natural log of x plus 3 minus the natural log of x plus 5. So try pausing the video here and see if you can find the solution for x to this equation. Like always, the first step is to get a single log on both sides of each equation. So this would be natural log of x divided by x plus 1 is equal to natural log of x plus 3 divided by x plus 5. Now we have a single natural log on both sides of the equation. So we can set the stuff inside equal to each other and start solving for x. So I'm going to multiply both sides by the common denominator of x plus 1 times x plus 5, which results in something you might have heard of before called cross multiplication. In other words, this x plus 1 ends up multiplied on the right, this x plus 5 ends up multiplied on the left, but it is just because of multiplying the common denominator on both sides. And now I'm going to multiply out. So the x times x plus 5, I'm going to distribute through to get x squared plus 5x. On the right-hand side, we need to FOIL. X plus 3 times x plus 1. So that would give us x squared plus 3x plus x would give us 4x, and then 3 times 1 would be a plus 3. What's going to happen is if you try to move one of the x squares around, they basically cancel each other out. If you subtract x squared from both sides, they're gone completely. And now we have a linear equation. So if I just subtract 4x from both sides, move that 4x over to the left, we just get 1x is equal to 3. Now we need to double check. If we plug in a positive 3, the inside of the first logarithm is positive 3, which is fine. The inside of the second would be positive 4, which is okay. Inside of the third would be positive 6, which is fine. And finally, we would have natural log of positive 8, which is okay. It doesn't make the inside of any natural log negative or 0, so we get to keep it. And so our final answer would just be 3. Now let's take a look at the final type of equation in this section. These are going to be logarithmic equations with constants. In other words, you have a +2, a +7, a -4 floating around on the outside of the logarithms. In that case, we have to take a slightly different approach. And in fact, we solve problems kind of like this as part of the swap and solve method of finding inverses in section 4.2. The trick is to write your equation in the form log base b of u is equal to c. And what I mean by that is you want a single logarithm on one side of the equation and a single constant on the other side. So you move all logarithms to one side and combine, move all constants to the other side and combine. What you do then, in order to get the variable outside of the logarithm, is you convert it to the equivalent exponential equation. So you bring down the base of b, the c moves across and becomes the exponent, and everything inside of the logarithm moves across to the other side of the equal sign. It's freed. Bring down the base, swap the position of the other two numbers. Once that's done, your variable is now on its own. You can solve for it. And then afterwards, as always when working logarithmic equations, check for extraneous solutions. This is the type of problem in this section that students seem to have the most trouble with. And I think the reason for that is you get used to working the logarithmic equations without constants, where you can imagine that you just make the logarithms disappear, although that's not actually what you're doing. You're setting the insides equal to each other. But very frequently, I'll see students get this setup, a single logarithm is equal to a single constant, and then they'll just make the logarithm disappear. That's not the way it works. The base here becomes the base of an exponential, which is very important. So let's take a look at some examples of logarithmic equations with constants. In part A of example 4, we've got common log of x squared minus 5x plus 6 is equal to 1. And again, so common, students will just take this and write x squared minus 5x plus 16 is equal to 1. Do not do that. What you need to do is, this already has the proper setup, one logarithm equal to one constant, we need to convert. So this is log base 10, so I'm going to bring the base of 10 down. The 1 comes across and becomes the exponent, and then everything inside of the logarithm, which would be the u from the previous slide, moves across to the other side of the equal sign. And so 10 to the first power is just 10. So we have 10 is equal to x squared minus 5x plus 16. So once again, quadratic equation. If I subtract 10 from both sides, this becomes 0 is equal to x squared minus 5x plus 6. And we can factor this. Two things that multiply to give a positive 6. If they multiply to give a positive number, the signs have to be the same. And so we're looking for a -3 and a -2. To double check, x squared minus 3x minus 2x would be a minus 5x. -3 times a -2 would be a plus 6. So it checks out. We're now going to set each of those equal to 0. And solve. So our two possible answers is +3 and +2. We do still need to double check and make sure that they keep the inside of the logarithm positive. So if we plug 3 in for x, we would have 3 squared or 9 minus 5 times 3 or 15 plus 16, which would be a positive 10. So that checks out, that's fine. And if we plug in 2, we would have 2 squared or 4 minus 5 times 2, or 10, plus 16, which is also fine. This plus 16 just overpowers that negative middle term no matter what, at least for our two solutions. So we're good. We get to keep both. So we have solutions of positive 2 and positive 3. Next up, we have a little bit of a different problem. And the reason why is because this time the variable that we're trying to solve for is the base of the logarithm. The process is still the same though. We want to get a single logarithm equal to a single constant, which again is already done in this case. So now we're going to convert. So I'm going to bring down the base of the logarithm, which is x in this case. The negative 1/2 moves over and becomes an exponent. And the 9 inside the logarithm moves over to the other side. So you have multiple choices as to how you work this problem now. You could turn that x into a 1 over x to the 1/2. And then think of that as 1 over square root of x and solve for there. I'm going to treat this like an equation with rational exponents, which we looked at back in section 1.6. I'm going to raise both sides to the reciprocal power. And the reciprocal of negative 1/2 would be negative 2. If I do that, multiply the exponents together, negative 1/2 times negative 2 would be a positive 1, or just x, which is the point. And then 9 to the negative second power would be 1 over 9 squared, or 1 over 81. Now we still have to check for extraneous solutions, but the rules are a little bit different when you're solving for the base of a logarithm. Although the number still has to be strictly positive, the base itself still has to be strictly positive, it also can't be equal to 1. But this is fine in this case, because 1 over 81 is a positive number, and it's not equal to 1. It satisfies the conditions to be a base. So it works for our solution. So next up, we've got log base 2 of x plus 10 is equal to 2. Try pausing the video here and see if you can solve this equation for x. All right, so I'm going to bring down the base. The 2 comes over to the other side. The x plus 10 moves across to the right. 2 squared would be 4. And now I'm going to subtract 10 from both sides. 4 minus 10 would give me negative 6. Now, I picked this particular example to illustrate a point. Sometimes students make the mistake of thinking that you can't have negative numbers as solutions. You can. What you can't have is a solution making the inside of a logarithm negative. If we plug this negative 6 in for x, we would have log base 2 of negative 6 plus 10, or positive 4. So even though x itself is negative, the inside of the logarithm is still positive. This is not an extraneous solution. Negative 6 works. Again, negative numbers can be solutions, but a solution cannot make the inside of a logarithm negative. That's the key. Next up, we've got log 4 is equal to 1 plus log x minus 1. So once again, try pausing the video here and see if you can solve this equation for x. All right, so we have to do a little bit of rearranging in this case because we need a single logarithm equal to a single constant before we can combine. So you can move the logs to the left, you can move the logs to the right, it doesn't matter, you'll always end up in the same place regardless. So let's say I subtract to the left. We're going to have log of 4 minus log of x minus 1 is equal to 1. Quotient rule, subtraction on the outside is division on the inside. And now this is the setup we can convert. I'm going to bring down the base of 10. The 1 moves over and becomes the exponent. The 4 over x minus 1 moves over to the right-hand side. All right, so now I want to get rid of the fractions. I'm going to multiply both sides by the common denominator of x minus 1. There's only one denominator. And then I'm going to distribute through to get rid of the parentheses. So we would have 10x minus 10 is equal to 4. If I add 10 to both sides, and then divide by the coefficient of 10, we get x is equal to 14 over 10, or 7/2 reduced. I should double check my answer. There's only one x in this equation. If we plug 7/2 back in, 7/2 is a bigger number than 1, right? 2 halves, 2 over 2 would be 1. This is bigger than that. So if we take 7/2 and subtract 1, it would still be positive. In fact, this would be 3.5. So 3.5 minus 1 would be 2.5, which is a positive number. So it doesn't make the inside of the logarithm negative. We get to keep it. So let's take a look at one more example. So one more time, try pausing the video here and see if you can solve this equation for x. All right, so going through this fairly quickly, combine both logarithms into one. Subtraction on the outside is division on the inside. Convert. 3 squared would be equal to x minus 6 over 2x. 3 squared being 9, of course. We want to get rid of the fraction, so I'm going to multiply both sides of the equation by the denominator of 2x. 9 times 2x would be 18x. Subtract x from both sides and combine like terms, and then divide both sides by the coefficient of 17. So we get a possible answer of x is equal to negative 6/17, which is a negative number. But you have to check and see, does it work? So if we plug this back in, if you took a negative number and you subtracted 6 from it, it would only make it more negative. So that's no good. Also in the other one, by the way, a negative number times 2 is still negative. So this x actually would make the inside of both logarithms negative, and it only takes 1. So we have to throw it out, which means we have no solutions left. The answer is no solution. This happens from time to time when you're solving logarithmic equations. If all of your answers end up being extraneous, then it is an equation with no solution. And that is it for section 4.4, logarithmic and exponential equations. As far as the types of problems go in this section, is basically the outline that we covered at the very beginning. There are 2 types of exponential equations, 2 types of logarithmic equations. You treat each one a little bit differently, so please be careful. This is a section that combines a lot of the stuff we were doing in previous sections, and because of that, this is a very important section in Chapter 4. You should not be surprised if at least a quarter of your upcoming exam, Test 4, is from this section alone. So make sure you don't sleep on it. Get plenty of practice. Make sure you master the types of equations in this section. It's very important. And also, do not forget to check for extraneous solutions for logarithmic equations. It's always easy to forget that, but it's a very important part of the process. As always, if you guys have any questions about the material, make sure you let me know, and I will see you in the next video.